All right, Nirav, you ready to go?
Yeah,
Yep.
thank you. Thank you very much for the introduction. So I'll talk about, as introduced, data parallel-based deep learning for model order reduction of parametric partial differential equations. So first of all, it is important to set up some context in this, in the context of what do I mean by parameter, in the context of my topic of talk. So parameter in general is anything that influences the solution. Let's say the most simplified manner. But in this talk, I will talk about the parameters in the sense of physical parameters, which affect our solution. For example, parameters enter into our domain in different forms. Let's say they could mean that different boundary conditions, different source terms, or different geometries. For example, different boundary condition may refer to the understanding the material response to changing boundary traction, or there could be different source terms, and we want to see that where to place the source term, like let's say heat source or heat sink in the domain, and we want to study the temperature profile with the change of with the placement of source term, or even more let's say involved parametrization is geometric parametrization, where the parameters define the shape and size of our domain, and we want to evaluate the solution field with respect to different shape and size, which could be used in for a structural optimization or different kind of shape optimization. And I will later on introduce an example about this. But in general, parameters enter into our governing system of equations, and we want to exploit the solution field with respect to change in parameter. And this is where model order reduction comes into play. As I said, our objective is to explore the solution manifold with respect to change in parameter. However, computing the finite element solution or the large scale system of equation will be computationally expensive, if not infeasible. And this is where we want to use the model order reduction to only represent the lower dimensional representation of the finite element solution, which can capture the parametric dependency. And often it turns out that there is a lower dimensional representation which can capture this parametric dependency. And we would like to use this representation and compute the solution in real time. But of course, it comes with some affordable compromise in accuracy because it is lower dimensional, so we have discarded something. In this context, let's say the model order reduction proceeds in general in two stages. One is the construction of the accurate reduced basis space, and the other stage is the quick computation of the reduced basis degrees of freedom, where the parameters where at different parameters we have to evaluate the reduced basis degrees of freedom corresponding to these parameters. So first of all, let's say there are many methods to construct the reduced basis space, and I will introduce here proper orthogonal decomposition, which is well established method. So the proper orthogonal decomposition works on compress and expose strategy, which means that it creates a snapshot matrix, which approximates the solution manifold within by taking into account the parameter variation into a parameter space. We construct a snapshot matrix and create a correlation matrix out of this snapshot matrix and perform the eigenvalue decomposition. Notice here is that while the inner product matrix is sparse, but our snapshot matrix is dense, so we are performing the eigenvalue decomposition of a dense matrix. And by using the linear combination from the linear combination of snapshots which we have already computed, we create a projection matrix, or let's say the map between the the finite element basis to the reduced basis space. And then we proceed to the second step, which is deep learning actually, where given a parameter, we want neural network to give us the reduced basis degrees of freedom. Now for the training of this neural network, which can compute the reduced basis degrees of freedom faster, we have to generate a lot of training data in the if you are using supervised learning, which involves computing many finite element solution and projection onto the reduced basis space, which gives us the input output data set, and we ask neural network by training it to learn the relationship between the input parameter and the output degrees of freedom. The advantage of using neural network is that it is non-intrusive method, which means that we do not need the access to the source code of the finite element solution technique. But and it is also efficient for the nonlinear problem. But the disadvantage is that the expensive training of the artificial neural network. And the expensive training is not the only thing that is costly. In general, we can say that we can split our operations into two phases: offline and online procedure. And offline phase itself is computationally expensive, but it consists of three parts. Let's say the computation of the finite element problem, performing the proper orthogonal decomposition, of performing the computing the eigenvalues, and the training of the artificial neural network. So I'm not, so in this talk, I'm only going to talk about the third part, which is the training of the artificial neural network. Now, once an artificial neural network is trained, we can give a parameter to the neural network, and it will give us the output degrees of freedom of the reduced basis solution. So till now, what I introduced is standard. It is not something that I claim to be our own development. However, what we have done is the distributing the artificial neural network training into the distributed training of the artificial neural network framework. So first of all, we have the data set. We have constructed a data set, and in the data parallel implementation, we split our data set into subsets which can be processed independent of each other. And we create the neural network, and we store the copy of this neural network in different processes, so such that the forward pass of the neural network and gradient computation, which we need during the learning process of the artificial neural network, can be done in parallel on each individual subsets. So these are the same neural networks or copy of the same neural network, but they are subjected to different data. And then before updating the parameters of the neural network, we do the gradient synchronization. So in a serial algorithm, we will do the forward pass and compute all this forward pass and gradient computation in serial. But here we split the forward pass and the gradient computation, but it comes at the cost of gradient synchronization once this is performed. And after the gradient synchronization, we perform the hyperparameter update. We can do further steps related to validation of the artificial neural network to check whether there is any overfitting of the neural network on the data set. Again, we can synchronize the loss and check if we want to continue the training, or we want to stop the training process. Now, so to this, let's say we are developing a framework which is DL-RBNX, which provides the functionalities related to the deep learning based reduced basis method. DL-RBNX is an open source library for deep learning based reduced order modeling, which means that it builds up above PhoenixX and the RBNX. So PhoenixX is being used mainly for computation of the finite element solutions. RBNX provides functionalities related to proper orthogonal decomposition and other some auxiliary functions for the reduced basis functional computations. And above that, we are adding the PyTorch based deep learning functionalities, which provides a simple interface for the user, and the PyTorch operations are taken care in the backend. And the DL-RBNX is divided into, let's say, in submodules, where we have different user-friendly interfaces for the activation functions, data set, neural network training and validation, etc. So basically, we have the custom data set, and it supports the serial training or a simple user interface for partitioning of the data set in CPU, as well as for the GPU training of the neural network. And the GPU training part takes care of the also of the transfer of the data set from the CPU to individual GPUs. Yeah. Similarly, for the training and validation, we have the training can be done in serial. It can also be divided into different CPUs or different GPUs, and the gradient synchronization and all the training, etc., is taken care of behind the backend, but user friendly interface. And the artificial neural network. So for example, in the case of neural POD-ANN based approach, we might have to do trial and error to identify that what is the optimal number of layers or the number of neurons, etc. So DL-RBNX provides a simple user interface to change it quickly from the front end, and also some other wrappers, for example, checkpointing, that if my neural network training is stopped due to some reason, then I can resume the training from the from the same point where it was abandoned. However, I must clarify here that this checkpointing does not take into account generating the same data, which means that it will be a different problem to generate the data using the Dolphin X or Phoenix X. So I must clarify here that this checkpointing does not refer to the checkpointing in the Dolphin X. And also setting up the process groups. So I'll quickly go through an example where we are optimizing the shape of the earth for the high temperature processes, and there are various geometric parameters involved, which says the geometric parameters are diameter or thickness of each section of the earth, which is made up of different materials. And we can compute the temperature faster with some of around 800 times faster with the relative error of the order of 10 to the power minus 2. Same is also for the displacement. There are demos model, but our aim is to go to the large scale models. And the further works that is being done in this area is about the autoencoder framework to reduce the dependence of the POD, which we know that does not work for many practical problems. For example, in the advection dominated problems. And with this, I would like to thank you for your time, and I'll be happy to answer your questions.